Okay, so good afternoon or good morning, everybody. So it's a great pleasure to have Nils Engelsen with us today. So Nils has performed his bachelor and his master degree for the latest was, you were awarded in 2010 in physics at the University of Cambridge. And then you cross the Atlantic and go to the United States, where you do your PhD in the group of Mark Kazevich in Stanford University. And you did some work that personally I really appreciated, I have to say, about spin squeeze states of atoms that's used for entanglement enhanced atomic sensor. So very promising work. And then you, I think you graduate your PhD in 2016, and then you somehow changed quite a bit of topics, and because you did a postdoc, and you are currently in postdoc actually since 2017 in the group of Tobias Kippenberg, EPFL, and then your current research focused on the development of ultra-high Q nanomechanical resonator and application to quantum optomechanical experiments. So I think that will be the topic of your talk today, if I'm not mistaken.
Yes.
So Nils, welcome, and then please, the floor is yours.
Yeah, thank you for the introduction and for inviting me to give this seminar. So I'm going to talk today about the kinds of structures that you see here on my first slide, which is a suspended thin film of silicon nitride. This thing you see is about 20 nanometers thick. The central segment is about 2 millimeters long. So these are extremely high aspect ratio devices. And what I'll show you is that the out-of-plane vibrational modes, so sort of the violin modes of this string, can have quality factors up to 1 billion or even exceeding it in the case of some other designs. But before I get into the details of the nanomechanics, I wanted to talk a bit about the first place where this effect was observed that allows these extremely high quality factors, and that was actually in LIGO. So as most of you know, LIGO is one of the biggest or the biggest optomechanics experiment in the world, where they can observe gravitational waves from billions of light years away. And what you can see is that they have this mirror suspension that I'm showing here on the right. And the mirror suspension actually displays this effect that we use in nanomechanics to make high Q, which is called dissipation dilution. So basically the stress from this large mirror increases the quality factor of the vibrational modes of the piano wire. And in nanomechanical resonators, we actually observe exactly the same effect, that the stress plus the nature of the modes that I'll get back to in a little bit combine to greatly increase the quality factor of these mechanical structures. So why might we be interested in this? Well, in using cavity optomechanical sensors, you can reach a wide range of application areas. For example, force sensing and spin detection can be done by detecting the motion of a mechanical resonator very accurately. They have also been used to engineer hybrid quantum systems and quantum transducers that can transduce quantum information from microwave domain to optical domain, as well as now for fundamental physics experiments like dark matter searches, and hopefully in the future to investigate quantum gravity. So how do these systems work? Just a brief introduction. Basically, a cavity optomechanical system consists of a cavity with a movable mirror. So this is the canonical picture of such systems. So the movable mirror moves. When it moves, it leads to a phase shift in the output field that we can detect with interferometry. And the radiation pressure from the light then pushes back on the mechanical resonator and can be used to manipulate and control the quantum state of this mechanical resonator. Near the cavity enhances the interaction strength. So where does the Q come in, the Q of the mechanical resonator? We will see this very soon. So first of all, what is the fundamental limit on how well we can detect position? This basically determines the sensitivity of all the applications that I showed earlier. This is the so-called standard quantum limit for position measurements. So when we want to detect the position of the resonator, we look at the phase of the light field. And how well we can determine the phase of that light field is limited by the photon shot noise. So the natural thing to do is to increase the power of our probe. And by increasing the power, we can determine the phase better and better. However, at the same time, there is this radiation pressure back action that I talked about earlier. So the quantum noise of the light field inside the cavity acts on the resonator and leads to a measurement back action on the position of the oscillator. And this means that there is actually an optimal power to probe the system, at which we reach the so-called standard quantum limit at about 2 times the 0-point fluctuations of this mechanical resonator. However, in most experiments, we're doing them at finite temperature. So in this case, there is also the Brownian motion of the mechanical resonator that enters through the coupling to the thermal bath. And this coupling rate to the thermal bath is set by the dissipation rate of the mechanical resonator. So this means that we have a Brownian motion noise floor here that usually greatly exceeds the standard quantum limit. And we have a thermal limited force sensitivity. So the smallest force we can measure is limited by the Brownian motion of the resonator. And as we can see, this thermal limited force sensitivity is of course affected by the temperature. But if we have a fixed temperature, like room temperature, where we want to measure, then the only thing we can affect is the mass and the dissipation rate of the resonator. And this, the quality factor of the mechanical resonator also sets the thermal decoherence rate. So how long can we expect the quantum state of the resonator to stick around if we manage to prepare it? And so what we want to do is to have both small mass and low dissipation. And these two requirements are usually in conflict. So the smaller the resonator is, usually the lower the quality factor is. This is mostly due to surface effects. So on the left here is a sort of survey of different kinds of mechanical resonators that we see as a rough Q versus volume scaling of V to the 1/3 power. And on the right, we can see that as we make silicon nitride films thinner and thinner, the Q actually decreases. But what we can see here on the left is that actually there seems to be some kind of trend here with these high tension resonators, that these are somehow breaking the trend a little bit. And actually, over the last 15 years, these high stress resonators have had their quality factor increase by about 4 orders of magnitude. So this is this dissipation dilution effect that I talked about earlier. So this effect, it greatly increases the quality factors of flexural modes. So these are the violin modes, for example, of stressed mechanical resonators. And this dissipation dilution factor that I call DQ can actually be affected by geometry. And it can be very large, up to 10 to the 5 or even 10 to the 6. So we can get with this effect mechanical quality factors that are up to 1 million times higher than the intrinsic material losses. And this factor can be engineered by geometry. And that's the kind of the trend that we see here, is that in the early years, they started out with simple strings and membranes. And then over the last decade, we have developed more exotic and sophisticated designs that lead to even higher quality factors than before, reaching up to 3.6 billion at room temperature. And the stars here are the resonators that I have worked on during my stay at EPFL. So how does this effect actually work? So it can actually be illustrated quite nicely by just looking at a simple 2-spring system. So if we take 2 springs and put a mass in the middle, and then we apply some tension on this system, we have two vibrational modes that are both harmonic oscillators, the X mode and the Y mode. And we can write down an equation for the spring elongation in terms of these X and Y mode amplitudes. And we see immediately that the spring elongation for the X mode is linear in X, and for the Y mode, it's quadratic in X. And this will turn out to be important. We can write down the classical Hamiltonian of the system and see indeed that it is a harmonic oscillator in the case where there is some tension applied. So you should note that this Y mode is actually a floppy mode unless we apply tension on the springs. Now, if we now introduce dissipation in the form of this Voigt damper, so basically just a dash pot in parallel to our spring that introduces a viscous damping force, we can consider this in the time domain or the Fourier domain that basically, as long as the losses are small, this Fourier transform holds, by the way, that there is a kind of a loss, there's a loss angle that we can call phi, which is sort of the lag between the force and the position, the elongation of the spring. And this is an analogy to the material loss angle or intrinsic loss of a material. We can now compute the quality factor of these two different kinds of vibrations by just computing the total stored power divided by the power dissipated, or the total stored energy, sorry, divided by the dissipated energy per cycle. So for the X mode, we get what we would probably expect, which is that the Q is equal to 1/phi, where phi is this loss angle from here. But for the Y mode, something different happens. And so for the Y mode, actually, the stored energy scales as y squared, while the losses scale as y to the fourth. So for small displacements in this idealized system, there is actually no dissipation, and the Q goes to infinity. And this is exactly what is happening in our nanomechanical resonators. The combination of stress, the tensioning of the springs, and what we call geometric nonlinearity, which is that the elongation of the material or of the springs is quadratic in the mode amplitude, gives this dissipation dilution effect. So in a real material, for example, this spring model of a uniform string, so this would be just a string with constant width, we can consider that the material has so this rotation part and bending part when we have some mode that's vibrating up and down like this. And actually only this bending part leads to dissipation, while the rotation part is dissipation free. So what we can also see is that the bending is strongest near the clamping points. So at the points where we hold the string or clamp the structure, there has to be a lot of curvature in the mode, which leads to this bending. And this mode curvature has to happen to match the hard clamp boundary condition at this point, where the mode amplitude and the mode derivative has to go to 0. And what is interesting is that this clamping region is actually very small for high aspect ratio structures. But nevertheless, most of the mechanical dissipation of such a vibrational mode happens at this clamping point. And we can compute then the dilution factor, so the quality factor of the device divided by the intrinsic quality factor for a string. And it has these alpha and beta factors that are geometry dependent. So they depend on the exact resonator geometry. And this alpha lambda factor comes from the curvature near the clamping points. And the beta lambda squared factor is from the distributed curvature over the entire mode of the mechanics. And this lambda is dependent on the aspect ratio. And for the kind of high aspect ratio structures that we make, it can be much smaller than 1. And this means that 1, this dissipation dilution factor is large, and 2, that this alpha lambda factor is completely dominant in the case of uniform strings and membranes. So the goal of any resonator geometry would then be to reduce this alpha factor. And that's what we have been doing at EPFL. So we've engineered a few different kinds of resonators that have a reduced alpha, which means that we want to localize the mode somehow away from the clamping points to realize a so-called soft clamping effect. So here I'm just showing you a sort of landscape of the quality factors accessible with different designs that I'll talk about today. So I'm going to start with this phononic crystal structure that was the first one chronologically that was realized. Just for, so you know, this is a plot of Q versus frequency for the theoretical model of these different designs, assuming some material parameters that are shown here. So an interesting aspect that you might note is that the intrinsic Q of silicon nitride of 20 nanometer thickness is only 2,600. But nevertheless, for the simple string structures, you can reach quality factors in the tens of millions. So even just the dissipation dilution effect itself with no fancy geometry gives you a very large enhancement of the quality factor. So how does this phononic crystal work? Well, what we want to do is to reduce the gradient at these clamping points. So what we do with a phononic crystal is that we pattern this regular periodic structure on a beam or membrane. So actually membranes were developed first in the group of Albert Schleiser in Copenhagen, where basically you make this phononic crystal that creates an acoustic band gap in the suspended structure. And this acoustic band gap doesn't allow propagation of modes within a certain frequency band. And then you make a defect in the center, so that would be this elongated part here in the string structure or the pad in the middle of this membrane. And around this defect, you can make a localized mode that then smoothly decays into the phononic crystal, and that therefore has a very low amplitude at the clamping points. So using this technique, you can completely eliminate this clamping curvature or clamping losses at the clamping points that I talked about earlier. So we took this phononic crystal technique a step further at EPFL. So we, in addition to making a phononic crystal in the beam, we also tapered the overall width of the beam to enhance the stress in the center. And this leads to even greater dissipation dilution than before. So by tapering the beam, we enhance the stress because the tension in the beam has to remain constant. We also have to change the periodicity of our phononic crystal since the speed of sound changes with the stress. And by combining this phononic crystal technique and the strain engineering technique, we reached the quality factors of 800 million at 1.3 megahertz. So here's a ring down measurement of this device where we measure the ringing down of the vibrational mode with an optical interferometer. And we see that it has a decay time of about 6-7 minutes for this 1.3 megahertz mode. What you can see is that also we did a stroboscopic measurement, which is to say that we turned the laser off for most of the measurements, such as not to drive or interfere with the decay of the vibrational mode. So this is a kind of technique that we use for all our quality factor measurements. Now, these structures that I just showed you are very large. So the devices that had the Q of 800 million were 7 millimeters long, and we can only work with a high order mode of the structure. This has disadvantages for certain kinds of sensing applications. So recently we also developed these what we call subacoustic wavelength soft clamping techniques, which are these string networks that I showed you earlier. So I'll first talk about this binary tree structure, which was on the title slide. So in the case of these hierarchical structures or binary tree structures, we can basically take a uniform string like this and make a branch with some angle theta. And it turns out that if you make such a branch in this tensile stressed structure, you get a wave derivative transformation over the branch where you reduce the gradient, the mode gradient, by a factor of cosine theta. So the bigger the opening angle of your branch, the more you reduce the gradient over the branch. So what we did is to cascade these branches to make this binary tree-like structure. And this binary tree-like structure actually has a soft clamped fundamental mode. So this can be highly beneficial for example, for optomechanics experiments, because the fundamental mode has the largest mode separation of the structure. So that means that you can look at this vibrational frequency, and it's very well separated from other modes that might interfere with your measurement. And we can see that if we plot the mode amplitude as a function of position, as we go out on these branches, the mode amplitude gets reduced more and more. So in this 1D representation, it looks like there are kinks in the mode. This is actually not the case. But compared to like a uniform beam where we would just have this usual sinusoidal shape that has a high gradient and high curvature at the clamping points. So we made a range of these structures with different number of branching points. So the more branches you have, the higher the quality factor should be. This trend is also generally observed in the experiment. So this is like a survey of many of the devices that we fabricated. And you can see that as we increase the branch number, the Q goes up, and also that we can reach with this technique quality factors up to 1 billion at room temperature at sort of 100 kilohertz frequencies. That would be completely inaccessible for a phononic crystal, for example, because to make a phononic crystal at this frequency, you would have to make your device maybe some tens of millimeters in spatial extent. And with the low thickness of 20 nanometers that we use here, that would be very difficult to fabricate. So for the best device, we have a fundamental mode quality factor of about 800 million at 107 kilohertz. So you can see here a 4-hour ring down of this mode where we have these brief strobes where we turn the light on to quickly measure the vibrational amplitude at different times. And we also show that we get enhanced quality factors also for some of the high order modes of the structure, and that for some of the devices it agrees very well with the expected from simulation, and with others there is some deviation that we have not yet understood. For the figures of merit of these structures, we get thermal decoherence rates at or these heating rates that I showed earlier of about 10 kilohertz at the room temperature and 100 hertz at 6 Kelvin, which is approaching the heating rates of trapped ion, of the best trapped ion traps. And the force sensitivities here are surpassing the best AFM cantilevers. So as a sort of physics perspective, these structures are interesting because of their fractal-like nature. And there is this famous mathematics question of whether you can hear the shape of a drum based on its spectrum. So we wanted to investigate how the mode density of this structure scales with dimensionality. So we measured this cumulative mode density, which is basically just counting all the modes below a certain frequency for a membrane and a string. So we find here that, as expected, the number of modes scales linearly with frequency for a string and quadratically with frequency for a membrane or a drum. But for this binary tree beam, it shows scaling somewhere in between the string and the drum. So they have a fractional spectral dimension. And as an aside, we can simulate very well the expected mode structure of this of the devices. And what we found is that actually, while the overall scaling of the experimentally measured data shown here in blue matches well to the scaling of the simulated data in green, we don't get the exact matching of all the modes with simulation. But we think this is because these extra modes that are there in addition to the string are sort of localized in the branches of the tree, and these modes can hybridize and change and get frequency shifts due to different kinds of fabrication imperfections. But nevertheless, the overall scaling is preserved. So we also use this hierarchical principle to make membranes. So membranes have the advantage over strings that they're very easy to interrogate optically inside the Fabry-Perot cavity. So we made the branching, the kind of the most trivial extension is to just take 2 binary trees and cross them and put a little pad in the middle. This also turns out to be the highest quality factor design, but it's very hard to fabricate. It breaks quite easily during the fabrication. So we also made this, what we call the steering wheel resonator, where we wrap the resonator on itself. So we take, when we make a branch, we link the branches like so. These devices also have increased quality factor for the fundamental mode compared to ordinary trampoline membranes that don't have these branches in the tethers. So with this, we reached quality factors of above 200 million at 100 kilohertz compared to previous results that were all below 100 million. Now, I showed you another design that exhibits this subacoustic wavelength soft clamping. And the advantage of this design is actually that it's even more compact compared to, so for the phononic crystal structures, we have to have many acoustic wavelengths of extent for the structure to achieve soft clamping. For the hierarchical structure, we don't need to have the structure be that big because we soft clamp the fundamental mode of the device. But actually these polygon resonators that I'm about to show you can be even more compact for the same quality factor and frequency than the fractal devices. So what we do here is we exploit the symmetry of these regular shaped polygons, which means that they have what we call a perimeter mode, so a mode that only exists on the perimeter of the mechanical resonator. And this means that it essentially doesn't see the clamps at all. So this boundary curvature that limits us is eliminated for these perimeter modes at the cost of some added torsional loss. So when the mode vibrates like this, it twists the tethers. So this is when you look at the tether from in the plane. So the tethers are twisted. This adds a bit of loss, but we still get a good enhancement due to this soft clamping effect. So what we see is that these perimeter modes can have quality factors exceeding 1 billion at room temperature, and also that they have high Q for the higher order perimeter modes. So this is an enhancement of about 2 orders of magnitude compared to a uniform string of the same size. So we made a range of devices with these polygons, also hexagons and octagons. And we saw that we get generally close to this theoretical bound shown here by the dashed line, and that this scaling goes as lambda squared, which means that the devices are soft clamped. So what you can see is that we're some ways away from this clampless limit. So this is the limit to the quality factor when all the boundary curvature is eliminated. And this clampless limit can actually be reached by phononic crystal devices. But to make a phononic crystal device at this 350 kilohertz frequency would again require a much larger spatial extent than is currently possible. So with these polygons, we can get the right scaling and go to quality factors of about 3.6 billion at 350 kilohertz. And this gives a force sensitivity of 420 septonewton per root hertz. So for according to some estimates, if you had the force sensitivity in the tens of septonewton per root hertz, you could sense the magnetic moment of a single proton with magnetic resonance force microscopy. So what you see here at the bottom is a ring down of this 3.6 billion Q mode that lasts for about 4 hours, taken in our setup at EPFL. We also made arrays of these perimeter modes, so they can actually be conveniently coupled to each other. So by having 2 polygons next to each other with a little tether in between, you can get a torsional coupling between the 2 modes of these structures. And this can actually be useful for different kinds of parametric sensing experiments. And we can tune the coupling between the 2 polygons by changing the width and length of the coupler. And we can then see that we get this frequency splitting between the in-phase and out-of-phase coupled modes of this system. We also made a chain just to show some kind of SSH model. So here we alternate the coupling between the polygons, and we see that we get these edge modes that are, and according to the simulation, we should get edge modes that have in either in phase or out of phase component at each edge. Unfortunately, due to the sort of noise and the frequency of these different polygons, with our edge modes are very much localized to one side. But it was a proof of principle demonstration of how we can make arrays and the dimers of these polygon resonators. So I said earlier that it's much easier to interrogate membranes optically than strings. And this is because the strings we make are very narrow. So the polygons, for example, are only 200 nanometers wide. So this means it's very difficult to make an optical spot that's small enough to get an appreciable reflection from the devices. While we can easily characterize their quality factors, it's maybe harder to do something useful with them with sort of free space optical interrogation. Now, what we did to help this is that we made an interaction pad in our polygon. So we widened the film at some point in the middle of the polygon up to here 2.5 microns. So this is accessible to light. We can make a spot that's smaller than that. And then we use our optical interferometer to interrogate the device, and we find that we have an SNR increase of about a factor of 3 or 4 at the point where we made this widening of the resonator. So with this, we wanted to make some proof of principle force sensitivity measurement. But when we first tried to do this, we were hindered by frequency drifts and alignment drift. So what we wanted to do here was just measure the position of our harmonic oscillator and use this to infer the external thermal force that pushes on it. Now, our line width here is about 100 microhertz. So if you have any frequency fluctuation, it will the resonance frequency will drift. And you will not be able to fully exploit the force sensitivity of the oscillator. So with this sort of naive measurement where we just take a long trace that's much longer than this 1/100 microhertz, so something like a 1 hour trace, we cannot reach the thermal limited force sensing limit. So we take this position measurement and turn it into a force measurement by the susceptibility of the oscillator. We are then prevented by these frequency fluctuations and alignment drift from reaching this limit. So what can we do about this? Well, we can apply some feedback damping. So if we measure the oscillator and apply a certain kind of feedback, so basically just a viscous feedback force, we can widen the frequency response of the mechanical resonator without adding extra noise. So we can get we can go from this very peak red susceptibility with a line width of 100 microhertz to a broadened susceptibility shown here in blue that has a line width of 1 hertz. So when we do this, we can much more easily measure the Brownian motion of the oscillator, and we then managed to reach the thermal limited force sensing limit of our device, which is here has a frequency of 227 kilohertz and Q of 1.5 billion. We then demonstrate a force sensitivity of 1.3 attonewton per root hertz at room temperature, which is approaching what the best AFM cantilevers can do, but they do it at dilution refrigerator temperatures, which are 10 to the 4 times colder than room temperature. So if we can take this device and cool it down, we will both get an increase of the quality factor and a reduction in this force sensitivity limit due to the reduced temperature. So how can we better interrogate these polygon resonators? I said that the small narrow structures are hard to interrogate with free space. So what we have done is to make integrated devices where we suspend a photonic crystal Fabry-Perot cavity next to the thin polygon string. And then the nanobeam can sit here in the near field of the optical field of this waveguide. And when it moves, it then changes the refractive index seen by this light, which shifts the cavity frequency, and we get our usual optomechanical Hamiltonian. So first a bit about these cavities. So we make a photonic crystal mirror on each side of the cavity to make a Fabry-Perot waveguide. We have shown that we can reach finesse here of about 100, and that we can then have line width of about 1.1 gigahertz. So these cavities seem to work pretty well. We also can engineer the coupling of our external waveguide to the cavity by changing the gap here between the two waveguides. So to explain, we use a tip-etched optical fiber to couple light into a waveguide that is suspended next to our Fabry-Perot cavity. And the light in this external waveguide then can couple into the cavity evanescently over this gap. And by changing the gap, we can change the coupling rate between the external waveguide and the cavity. And we show that we can get very efficient outcoupling of the light from the cavity. So we can have a much higher coupling rate between the external waveguide than the intrinsic losses of this cavity, which lets us have very high detection efficiency. This detection efficiency is, of course, a very important parameter for doing quantum optomechanics, because we want to get, if you want to, for example, cool this oscillator to the ground state, we need to collect as many photons as possible from our cavity. And by tuning the gap, we can tune from overcoupled, where the coupling rate is much higher than the intrinsic loss, to undercoupled, where the coupling rate is much lower than the intrinsic loss of the cavity. So combining this photonic crystal cavity with a mechanical resonator, we have reached a quality factor of 120 million. So we have to use here slightly smaller polygons than we did for the pure mechanical resonator work, because the gaps between the photonic crystal cavity and the nanobeam is only about 200 nanometers. So it's very easy for them to stick together during the fabrication. And the bigger the polygon is, the more likely it is to stick. But nevertheless, this is a very high quality factor for an integrated device. And we showed that we can get also high optomechanical coupling rates. Combined with low line mechanical and optical line width to reach cooperativities of about 123. And this number basically means that our coherent coupling to light is much stronger than the dissipative processes in the system. And ordinarily, this should be a suitable candidate for doing ground state cooling of these mechanical resonators, even from room temperature. But what you can see in this spectrum that I'm showing here is that there are these other parasitic modes. So these, like this one, is an in-plane mode of the polygon, as well as this. And these other modes contaminate the spectrum with their Brownian motion, which means that actually with this particular device, it's not possible yet to do ground state cooling. So this is something that we're still working on. And we're probably going to try those fractal devices I showed you earlier. So going back to our quality factor landscape, I've just explained to you the different designs that we've developed. But as I mentioned, silicon nitride has a very low intrinsic quality factor. So this dissipation dilution effect is a material independent effect, right? So if we find a better material with higher intrinsic Q, we should be able to get even higher quality factors than before. So we started the project working on strained silicon-on-insulator. So strained silicon is basically just silicon with a stress applied. This is a crystalline material, so potentially it can have much higher intrinsic quality factors at low temperature in particular. And this is a transmission electron microscope cross-section of the kind of wafers we used for this project, where there is a 11 nanometer thick silicon layer on top of 100 nanometers of silicon oxide, again on top of silicon. And this you can show by dark field electron holography, where you essentially interfere electron scattering from the top layer with the electron scattering from the bottom layer, that this layer here is under about 1% of strain. So we have our stressed material, and we developed a fabrication process to make up to 6 millimeter long, 12 nanometer thick silicon strings. And we made these soft clamped beams, similar design to what I showed you earlier. These have this acoustic bandgap. There's a localized defect mode inside the bandgap due to the defect in the center. When we measured this string at the room temperature, we can infer a quality factor of up to 1.5 billion, which we couldn't quite measure because the pressure of our vacuum chamber was too high. So still at 210 to the -7 millibar, it was still damped by gas, the residual gas in the chamber. Fortunately, we can cool this chamber down to 7 Kelvin. At 7 Kelvin, we found quality factors of 13 billion at 1.4 megahertz, which gives this ring down time of about 2 hours. You can see here very clearly the effect of this soft clamping with the phononic crystal. So all the modes outside the bandgap have Qs of almost 10 to the 8, or exceeding it a little bit as we approach the bandgap. While the mode inside the bandgap has Q here of 13 billion. So to give the figures of merit from this, you can have a thermal decoherence rate or heating rate of 10 Hertz and a force sensitivity of 50 septonewton per root Hertz. For a mechanical resonator that is actually anchored to a substrate, this number is well in excess of anything that has been measured before at these temperatures. We also looked then at the mechanical dissipation properties of silicon as a function of temperature. We saw that there are these dissipation peaks that are likely due to some kind of thermally activated two-level system. So the vibrations of the mechanical mode leads to some configurational change inside the material that leads to losses. So we investigated this in some detail, these dissipation peaks, and found that actually we wanted to see if for different modes the peak will occur at different temperature. And we found a weak frequency dependence of this thermally activated peak, which is something you would expect from sort of this kind of two-level system-based dissipation. Another thing to note is that actually the ratio of the quality factor of the localized mode to the non-localized mode changes with temperature, which is something you wouldn't normally expect. You would expect it to be constant and equal to what it should be at room temperature. But we believe that this is because at these clamping points, there is an oxide layer in close proximity to the beam. This is only seen by the non-localized modes, but not by the localized mode. So the localized mode only sees the dissipation of the silicon itself, whereas the non-localized mode also sees the mechanical dissipation of the oxide. And this oxide has much higher dissipation than the silicon, especially at low temperature. So this is another benefit of the phononic crystal in this case. So as a sort of outlook, I want to just briefly mention a couple of applications that I think are interesting. We have made these polygon devices that have extremely high quality factors and therefore very low force sensitivity. So at 20 millikelvin, even if we don't account for the increase in mechanical quality factor that should happen when you cool down to such low temperature, we could reach force sensitivities on the single-digit septonewtons per root hertz, which is much better than any other system to date, at least any sort of bulk mechanical system like this. And you could make molecular maps of different kinds of biomolecules using magnetic resonance force microscopy techniques. And the polygons are especially well suited for this because this tip and sample would usually interfere with your interrogation, optical interrogation. But we have a natural separation of those two areas for this design. And there's actually been some initial work on using silicon nitride resonators for force microscopy, where they use membranes instead of strings. But we want to now investigate how it can be done with strings, since the strings have much lower effective mass than membranes and therefore higher force sensitivities. Another interesting venue is to try to functionalize one side of the polygon resonator. So if you can put here like a nanomagnet, you can use this to do nano MRI. Or if you can metalize this side, you can make these quantum transducers from microwave to optical domain. Or you can put the other materials here that would enable you to couple to other quantum systems. So currently, silicon nitride is a dielectric, so it doesn't couple well to a sort of electric and magnetic fields, but by depositing, for example, metal or magnets, you can potentially change this. And it has been shown in the literature that actually such manipulation of the resonators does not necessarily degrade the quality factor too much. There's always some degradation, but not to a prohibitive extent. So that summarizes my talk for today. So all the work that I showed you was done in collaboration with people at EPFL. Mohammed Berei made the polygon resonators that I showed. Sergey contributed a lot on the design side. Diego measured all the strained silicon devices that were fabricated by Alberto. And Amirali and Guanhao contributed on the measurement side. And all the work was done in the lab of Tobias Kittenberg. And if you're interested in learning more about how we do the fabrication, you should check out our open science platform, NanoFabNet, where we publish our full nanofabrication recipes with the complete detail. So thank you very much for your attention.
Thank you, Nils, for this very nice talks. So I guess session is open for questions. So please raise your hand or unmute yourself. Nils will be happy, I guess, to answer to your questions.
Yes, of course.
Okay, maybe I will start by one question. I mean, or let's say two questions. I mean, the first one is this clampless limit that you show. I mean, earlier in your slide, so it's scaled like lambda square, if I'm not mistaken. But I missed if you give the argument, why is it scaling that way? I mean, did you give the argument, or maybe I miss it? I don't remember. So that's my first question. My second question is more technical. I will say is that I mean, how good should be all the strings somehow in order to have such a high quality factor? I mean, if there is some imperfection in the fabrication, I guess the quality factor should decrease quite a bit, right? So that's my first two questions. What do you say? Okay,
so starting with the first question, basically, if you solve the Euler-Bernoulli equation for a beam, uniform beam, you can find that for a high aspect ratio beam, which is here to say it's very thin compared to the length, you can divide the beam into two domains, where there is the distributed domain and the area near the clamping boundary. And in the clamping boundary, the solution of the mode shape of the beam will be an exponential function to match the boundary condition at the clamping point, whereas the distributed mode is a sine wave. And if you take these two parts and integrate the over their spatial extent to find the so-called bending energy, which is proportional to the curvature of the mode shape. You get these two contributions in the dilution factor. With the first one is here, this alpha lambda factor. So that comes from the boundary area. And then you get this lambda squared contribution that comes from the distributed mode area mode. So if you had a clampless beam, it would just have a sine wave mode shape, an infinitely long sine wave mode shape, and it would therefore have a dilution factor going as lambda squared.
I understand. Okay.
So the full argument can be found in this PRB paper.
Okay.
And for the second question, you asked me if there is contamination, will it degrade the Q? The answer is generally yes. Let me show you some of the data. So if you look at this, for example, this survey of quality factors, you can see that only some of our devices reach the simulated Q. And even this is a selection of all the Qs that we measured. It includes most of them, but some of them, if there is a big piece of junk, it will be very low, like 100,000 instead of 10 to the 9. So yes, it's very important to have very clean fabrication, and certainly if there is visible contamination, it will be very greatly deteriorate the Q.
I see. Yes. Okay. Okay. Any other questions? So please. Okay, let me ask another question. You in the title of your talk, you about quantum optomechanics, and then you mentioned several times, some application related to that, and then you say also that you need to somehow cool this to the 0-point energy of the oscillator, basically.
Yes.
I guess more the frequency is lower, right? Harder is the objective. Is it? This argument is correct? Just and then, so can you give us a little bit more ideas of how we can cool that, and even at room temperature, if I understood you correctly, right?
Yeah. So let me find this slide. Yes. Basically, the way that we can cool these oscillators is by feedback. So we measure their position and act back on them to cool them down. If it's harder at low frequencies, mainly because at high frequency you can usually operate in the so-called result sideband limit, where the line width of your optical cavity is lower than the mechanical frequency. And this means you don't need to do this feedback cooling, which is a bit more tricky in terms of technical aspects like noise of your laser and detection efficiency. So that's why it was actually only in 2018 that for the first time someone feedback cooled the mechanical resonator to the ground state. Although ground state cooling of other mechanical resonators was achieved in about 2010. So yes, it's harder with low frequency. So far, no one has feedback cooled this kind of resonator to the ground state from room temperature due to the extreme requirements on the quality factor of the device. Yeah, so does it answer your question? I think I'm
sure.
A little bit.
But is it something that you are trying in the labs, or you are more focusing somehow on developing the resonator itself?
Right. So yes, it's something that we're trying in the lab, mostly in the form of these integrated devices, but also with the membrane in the middle experiment that we have. So the main goal of this integration with this photonic crystal cavity is actually to cool to the ground state from room temperature. And we think that should be possible because, well, with this system, we get very high coupling rates from this near field interaction between the nanobeam and the cavity. And we can get these extremely high quality factors. The current generation of devices probably cannot do it, but we still think that if we, instead of a polygon, put here a binary tree beam, like the one I showed earlier, that this can be a suitable system for feedback cooling, at least close to the ground state from room temperature. And
for this feedback cooling method, I mean, the quality factor or the fineness of the optical cavity, is it an important parameter?
Yes, both are important. So first of all, there is a requirement on the quality factor times frequency product of the resonator. So the way to think about this is that when you want to cool the resonator down, basically you broaden its line width. We need in the ground state, the resonator should still have a line width that's lower than its frequency. Otherwise, it's not really an oscillator anymore. And this sets a requirement on the QF product of the resonator. And this is actually quite stringent. So it was only like 10-15 years ago that someone made a resonator that satisfied this requirement at room temperature. The resonators we make very well satisfy this requirement. In addition to that, of course, the dissipation comes in the cooperativity parameter. And in order to feedback cool to the ground state, you actually have to satisfy a more stringent requirement than just having this cooperativity be greater than 1. You need the so-called quantum cooperativity to be greater than 1. And this means that the coherent coupling rate to the light has to be greater than the thermal decoherence rate of the oscillator. And the thermal decoherence rate of the oscillator is set by the Q.
I see. Okay, understood. Okay, so any other question from the audience? So I think it's a very new topic for us, very exciting as well. So maybe people are shy to ask questions on topic that they are not mastering very well. I'm not shy, actually, personally. Okay, so Nils, if there is no other question, thank you very much for this very nice talk, very interesting talk, and hope to see you around Singapore sooner or later.
Yeah, thanks.
Okay, thank you. Bye-bye.
Okay, thank you. Bye.